Now for the third and final law, Newton's third law. So what Newton's third law says is that whenever one object exerts a force on a second object, the second object exerts an equal and opposite force on the first. So another way that some people state this is for every action, there's an equal and opposite reaction. So all forces act in pairs, basically. So every action that you have that you do against another object is going to have an equal and opposite reaction back. So for anything that's not moving. Now this is not always the case. If you have something moving, they're not going to be equal because you're causing unbalanced forces. But the picture there shows you somebody skateboarding. Now that person's foot is pushing off on the ground. That's the action. The reaction is that the ground is pushing back on you. Now, obviously, the ground does not have a brain. It does not have the ability to think and purposely push back, but the force that it has and its mass that it has allows it to push back. Now, if it didn't push back, your foot would go straight through the ground, and obviously that does not happen. I know this is a concept that, if of all three laws, it throws people off, but this is how, this is what makes the world able to, all physics is what makes the world able to function, but if you did not have these equal and opposite reactions, you wouldn't be able to stand on the ground, you wouldn't be able to walk, you would not be able to lean against a wall, because if they weren't pushing back with equal and opposite force, you would fall right through all these things. So that's how we know these things, that this law is true. Force pairs do not act on the same object, and that is something very important to remember. Remember that we have an action and a reaction. We have, let's say, if you have somebody's foot pushing into the ground and the ground pushing on the foot, one is acting on the foot, one's acting on the ground. If you have a pair, they're acting against each other, because if they weren't and they were both acting on the same object, they would be acting, if they're acting on the same object, the net force would balance out to zero, because if one's pushing with equal force one way and one's pushing with equal force on the other, that object would never be able to move because of the balanced out net force. So if you're walking, your foot pushes the ground pushes on the foot. If you are leaning against a wall, your body is pushing against the wall, then the wall is pushing against the body. That's what causes, that's what your force pairs actually are. So an object that is falling is going to also experience reaction pairs too. So if you drop an object, we've talked about objects that are in free fall, and one force, the force that's pulling it down, is gravity. So it's pulling it towards the Earth. We've also talked about gravity and orbit and stuff like that, and we've talked about how gravity is the attraction between the center of the masses of two objects. So when the Earth is pulling the ball towards it, the ball is technically also pulling the Earth back towards the ball. So the Earth pulls the ball towards it, and the ball pulls the Earth back towards it. Now, obviously the Earth is a lot bigger than a ball. The Earth's gravity is so strong that you notice the falling of the ball. The ball is falling towards the Earth because its gravity is so strong. The ball is not strong enough to actually physically move the Earth, but it does have that pull. Now remember, we've talked about this with gravity. You don't notice them a lot of times. You do not notice most gravitational attractions that are out there, but it is happening. So when a ball's falling, it's technically pulling the Earth back towards it. It just doesn't have a strong enough pull for it to actually do any kind of damage. A property that is associated with Newton's third law is something called momentum. So momentum is a property of a moving object that depends on the mass and the velocity. So the more momentum an object has, the harder it is to stop that object, and the harder it is to change its object. So we talked about inertia with the first law, but if we look back at that and we think about the Prius and the semi, as those objects both get moving, the semi is going to have more momentum because it has a bigger mass. Even if they're going the same velocity, it has a bigger mass, so it's definitely going to have more momentum, which makes it harder to have it turn or to stop it or to keep speeding it up. Now, if you had two semis, let's say, and one is going 20 miles per hour and one is going 60 miles per hour, that 60 mile per hour vehicle, that semi, is going to have more momentum because it has a higher velocity. So it's harder to slow it down, and it's harder for it to change direction in a way with a semi that it wouldn't tip over. So momentum is what keeps when the more momentum, the harder it is to change both the direction and the speed depending on its velocity and its mass. So we have a law that applies to momentum that says when a moving object hits another object, some or all the momentum of the first object is transferred to the other. So the two best examples that we have of this is thinking of playing pool, like billiards, or bowling. So if you've ever played pool, I guess most of you probably have attempted it. You hit the cue ball, and then that cue ball hits your goal, hopefully, is to hit another ball. So if you hit that cue ball, you're transferring your momentum of your pool stick to that ball. That's what causes it to move. So your pool stick is either going to stop completely or it might move just a little bit. So if it stops completely, that means it transferred all of its momentum to the cue ball. If it moved a little bit more, that means it didn't transfer all but most of it. Then that cue ball, in turn, hits another ball. So sometimes that cue ball stops right in its tracks when it hits the other ball, and that means that all of the momentum from the cue ball is transferred. And sometimes the cue ball is going to move a little bit more, which again means that most of its momentum was transferred. But either way, if you run into another object, then that's going to cause most of that momentum to be transferred and cause that object to move. So an example, real life example of this would be us teachers, the high school teachers, play hockey at lunch. We play real hockey when there's the hockey unit in PE. So in the past, when we have played, I'm not exactly the biggest teacher on the hockey court. So when I try to play and I might get shoulder checked, let's say by someone like Mr. Andrews, who has definitely checked me before, the momentum of his mass is transferred to mine. So instead of me being able to stay in my spot, his momentum is transferred and it causes me to go flying instead. So that is examples of momentum being transferred in with humans in real life examples. So his running, he hit me, he stopped, and all his momentum went to me, which then caused me to fly in the direction he was running. So that is momentum. But if it doesn't get transferred to second object, it stays with the first. So that is essentially what law of conservation momentum is. It's not just going to disappear, it's going to be transferred from one object to the next. So we just talked about the cue ball hitting the 8 ball or whatever ball you're hitting. But just to kind of pair that up with Newton's third law is talking about the reaction and action pair force. The action force of the cue ball is that it's hitting the 8 ball, and that caused it to move. The 8 ball hits the cue ball back, and that's what causes it to stop. So that's why momentum is tied in with the third law, because those action-reaction forces is what causes the momentum to be conserved and it to be passed on to that other object that it's hitting.